on the road. Okay. So we're going through first order circuits, and we talked about how to analyze any first order circuit. Any first order circuit is a circuit that has an equivalent capacitor or an equivalent inductor. And obviously you can have a bunch of resistors, but we can't have two charge storage devices, capacitors or inductors, and treat it as a first order. That's a second order circuit or higher, could even be higher. And so we would have to do different circuit analysis techniques to do that. So we are now looking at adding the concept, and this is just a mathematical construct, which it makes our analysis a lot easier if you understand what these functions are. And so it's called a unit step function, which is just another way to actually add a switch. So a DC source, you go from 0 to whatever the DC value is at usually time t equals 0. That is mimicked by our unit step. So instead of having a circuit with a switch transitioning at t equals 0, normally what we would do is we would specify a unit step input for a power supply. So what I would mean is, here's our power supply, and then we would put U of t to indicate that that power supply only gets turned on at time t equals 0. That's all that that represents, okay? And from a curve perspective, we can see the curve on the left. A unit step is 1 unit in length. So it goes from 0 up to 1, and it stays fixed at 1. It could be volts, it could be amps, it doesn't necessarily matter. This is just a unitless quantity, and it shows that it represents there. If you were trying to mathematically write this, you say that U equals 1 or 0 for t greater than or equal to 0, and is equal to 0 for t less than 0, okay? And this is if we delay it. So let's just say for some reason you have a switch that transition or a power supply that transitions, and you have a delay associated with it for one reason or another. We can add in the minus t naught there. Why is it minus t naught? Because you can see that this is positive t over here. Why do we call that minus t naught and not t naught? Why don't we put a plus right here? What helps me kind of evaluate it is whenever this is 0 or greater, right? 1, 2, 3, 4, 5, then that's going to evaluate to an actual function. Whenever it is 0 or less, then this is actually going to be 0, right? The output's 0. So you can see if I pick a point over here, let's call that point A, then U of A is going to be equal to 0, right? It doesn't have any output. So that's why when you delay a function, you are subtracting it because it doesn't actually start taking into account until whatever that t minus t naught evaluates to being 0 or greater than 0. That's why we always subtract it. So here is a way to represent it. You can see the image on the left, which shows what the unit step would be with a slight delay. And it shows that it's a 5-volt source, and it's delayed by 0.2 seconds. If we wanted to represent that with a switch, you can see that our switch is open until we get to 0.2 seconds, and then the switch closes in. If you want to do it even more accurately, does everybody know what a double throw switch is? It's sort of a make before break condition, right? So you would transition over, and then you would get that condition. So the first case, it's break before make, right? So you have to open it up before you transition. Over here, I'm connected. The circuit is always grounded, forcing it at 0 volts. And then I actually connect it to the 5-volt source. And then at that point, I open the circuit, okay? So that is a double throw configuration where you have to do a make before break type configuration. So the reason why is this is not, it's an open circuit, right? So your network is not discharging. This over here is actually not showing that that's at 0 volts, right? because it's not connected to anything, so your circuit isn't necessarily de-energizing. Where in this case, I am actually discharging my system through that short. Okay? So that's where it has a very different impact. We can do pulse waves. So you can see that I have a rectangular pulse, and that just means it's 2 unit steps, right? I have 1 unit step that kicks on over here, and another unit step that kicks on at T1, but it is minus V naught, right? So a rectangular waveform, V of T, is equal to V naught times my unit step, T minus T0, plus negative V naught, that's a U, U of T minus T1. That's how you can go ahead and build a rectangular waveform. You just have 2 unit steps. They subtract from each other at whatever time. The sine wave is a little more difficult because you actually are not doing anything until here, right? So we're not going to necessarily represent that. And the likelihood is that you're probably, unless you're really into like communications where you actually have to do, pulse width modulation on signals like this, you probably don't have to worry too much about something that looks like this. So, all right, so now we're going to actually take our circuits that were initially either charged or uncharged, and we're going to try to get this circuit, and we're going to drive it to a specific voltage and see what the output is going to be. In this case, we're looking at the voltage across the capacitor, and that's our output. So we close our switch at time t equals 0, and you can go ahead and you can analyze our circuit, right, with the switch in the open position, and then you can do the same thing once the circuit is energized. So instead of showing it as a switch, I can actually add the U of T. And the circuit has 2 responses. It has a natural response. The natural response is the circuit naturally either de-energizing or energizing. But it also has a forced response, and the forced response is due to the power supply. So a natural response is just the system naturally doing what it needs to do because there's no external driver. And the forced response is because you actually are forcing it to a value. We'll talk more and more about that throughout the semester when we get into like looking at exponentially decaying functions versus steady state functions that continue to exist. So if we wanted to replicate our voltage, right, we know, or hopefully we know, that the voltage across the capacitor, VC, if it's initially uncharged, is going to be 0. And then eventually, what does that capacitor do when it becomes steady state? What happens to a capacitor when it's fully charged? It becomes an open circuit, right? No more charge going in there because you can't stuff it in there. So over time, this transitions to an open circuit, which means that in steady state or its final value, its voltage is going to become V0. So how do we represent that? With a waveform. Start out at 0. We end up at V naught. And if you remember from time constants, it takes 1 time constant to reach about 63% of its final value. So we can write an equation. The voltage across the capacitor is going to be equal to the natural response plus the forced response. The natural response is what the capacitor is going to look like as it charges. That's e to the minus t over tau. And we also have this constant A, and that's the initial condition, right? We can determine A by the initial condition. So what is it naturally doing? It's got no voltage initially, so that value would be 0. And then our final value is going to go to some constant K, right? Because there's no oscillatory nature. There's no decaying exponential. So that is just going to be a steady state value. So we can call that K. So our final function for voltage is V naught times 1 e to the minus t over RC. So here is the part of the approach to solve for any driven RC circuit. You want to find R equivalent and C equivalent so that you can solve for your time constant. You're going to determine your initial condition V near 0 plus or I 0 plus. And remember, V 0 plus is the same as V 0 minus, right? So these two equal each other, but these two do not equal each other, right? So we have to be careful when we're solving for our initial conditions, what can change instantaneously. Our final condition, it doesn't matter. It's this, the circuit is the same, so everything's reached steady state. So we have V infinity or I of infinity, and then we just plug into our first order equations. All right, let's do an example. So given this is a driven circuit, we want to find I of t and VC of t after the switch transitions from position A to position B. And we're going to assume that that transition from A to B happens fast enough that you don't really have any circuit discharge, nothing wonky happening. So it's almost happening instantaneously. So why do we want to do the switch transitioning from A to B? Why do you think that is written in there? Switch transition from A to B. Any thoughts? Bless you. Because I don't want to, go ahead, Luke.
Could it mean that capacitors will start?
Yeah, I want to find an initial condition on the capacitor that's not zero. So I want to have to do a little bit of work to solve for this particular circuit when its initial condition is not zero. And then I switch to B, and then B has a different voltage source. So then its final value is going to look different. And by the way, which one do you think is going to be higher capacitor voltage? Is it going to be the initial condition or the final condition? Or you're not sure? Luke?
I would say
Why? Yeah, the just first blush looking at it is because I've got a 120 volt source as opposed to a 50 volt source. The thought is that it's going to likely have a higher initial voltage than its steady state final voltage. So this circuit's most likely going to discharge. Okay. All right, everybody understand what we're doing? All right. Let's build the circuit in position A. This is what the circuit looks like. What happened to my capacitor? Capacitor's not there. You can see it here, but why isn't it here in this capacitor? I mean, in this circuit. It's fully charged, so what does that mean? It's an open circuit. So I don't have to show the capacitor when I'm calculating the initial condition voltage, do I? Because it's fully charged, so there's nothing going to it. So electrically speaking, yes, the capacitor is physically still there, but it's not acting as a load at that point. So all I need to do to figure out its voltage, which is here, is solve for the voltage drop across the 50 ohm resistor. You can see that they're in parallel here in the original circuit. So I just need to calculate the 50 ohm resistor voltage. I got 100 volts. Now I'm going to redraw the circuit in the final condition, which means the 120 volt and the 10 ohm resistor, those are both gone. And now I'm left with the 50 volt, 60 ohm, and 200 ohm sources. So let's build that circuit. And does anybody have any issue how I redrew it a little bit? Because up here, it looks like the 60 and the 200 are in parallel, but they're not, right? The 60 and the 50 volt source are in series with each other, and then they're in parallel. So I just kind of drew it to make it a little more obvious. Remember when we started the semester, the best thing you can do is redraw your circuits to make them easier to analyze. So I just did it that way. I just did 2 nodes. And then I can go ahead and solve for my Z. of infinity. Sure. Any questions on that? What I did to go from here to here, this is in position A. This is in position B for the switch, right? Those are the two different positions. So now I have another voltage divider if I put these two in parallel with each other, which is not a hard calculation. So I just showed you that to get the voltage across that, I just put the parallel combination. That's why I did 200 in parallel with 50 as shown, and then I get 20 volts. So I'm feeling pretty comfortable because when I started the problem, I said, I think the voltage is going to be higher for the initial condition than for the final condition. And then that is kind of indicating that that's the case right here. We start out with 100 and then we go down to 20. So now this is where it gets to be much harder. But do you remember the process when I'm solving for current in a capacitor, because it can change instantaneously, I have to calculate the voltage just before the switch transitions. So I know what my circuit looks like. You notice that I put the 100-volt source in there. And I put that in there because, again, the voltage across the capacitor can't change instantaneously, but the current can. So I put my voltage source in there to now go ahead and calculate what the current will be. So this current has to be calculated out of there. So let's go back over here. I'm looking for I of t, not IC, but I of t, right? Which is through the 200 ohm resistor. And I can see that this is the I of t that I'm looking for. So I got 100 volts across the 200 ohm resistor. That's happening. Okay, that's really important to make sure you understand the process, is that I've got to go ahead and calculate the initial condition for the voltage first before I can calculate the current. I cannot calculate the current otherwise, or accurately calculate it, maybe is a better way to say it. Henry.
Did you have to take into consideration of other volts?
Sure, and I am. The question from one of your classmates is, do you have to take into account the 50-volt source? And the answer is yes, and I have. This whole node is 100 volts, right? So what that means is that initially, that capacitor is going to be feeding some current into the 50-volt ideal source, right? So for a very brief instant in time, I'm actually dumping electrons into that 50-volt source. But that's okay, because the capacitor's job in life, right, is to store electrons or then send them back. So yes, I am taking into account, but it doesn't matter because the voltage across it is higher. So that ideal voltage source acts like a battery at that point. It's taking power in. All right, so now I've got to find I of infinity. And I of infinity is here, right? Now you might be saying, well, how do I end up with this value over here? So this one, I got to go back in here and I got to look and see my voltage across there is 20 volts. I could certainly go ahead and recalculate it, but the voltage from this point to this point, it doesn't matter if the capacitor is there or not. So my previous one is I calculated 20 volts. So 20 divided by 200 is 0.1 amps, or a tenth of an amp. So let's go back. I've got V0 minus plus, that's 100. VC of infinity, that is 20. I have I of 0 plus, that's 0.5. And I of infinity, which is 0.1. So I have all four of the parameters that I need to start to build my voltage and current equations. The only thing I need is my time constant. So I've got one capacitor. So all I need to do is look out and from the world, and what does this capacitor see? Not in position A, but in position B, right? Position A, I don't care about. I've assumed that that is fully charged the capacitor, so I'm not focused on any time constant. I'm only worried about it being in position B. So this here, little power supply, a 50-volt power supply, gets replaced by a short circuit. So what I have is a 50 in parallel with a 200 in parallel with a 60 ohm resistor. And there's no product over sum that works well for that. So I just did the inversion and I ended up with 24 ohms. So then my time constant is just RC, which when you take 24 and you multiply it by 50 millihenry or 0.05, you end up with 1.2 seconds. So now I have all 5 of my parameters. I have tau, the 2 voltages, initial and final condition, and the 2 currents, initial and final condition. So I can just build my final equations. There's my VC of t, kind of spelled out and then simplified. And then there's my I of t, spelled out and simplified. Questions? I'm just solving for the Thevenin equivalent. So I'm looking for what this capacitor sees when the circuit is in position B. So to solve for Thevenin equivalence, right, you replace all ideal sources by their internal equivalent impedances, which means I replace that voltage source. I didn't actually short it out. I just replaced it with a short circuit. And then that it just had the 3 resistors in series or in parallel with each other. And that's what I end up with. Make sense? Here are the plots. Here's my voltage, right? So we don't know how long the voltage was at 100 volts or is at 100 volts before time t equals 0 from the switch transition perspective is. But we can see that it started out at 100 and it discharges and gets to 20 volts in steady state. Now, current is a little bit different. The current was happily running along, and I didn't even calculate this value over here. How about I give you 4 minutes? Go ahead and calculate 192 milliamps. Can you go ahead and calculate it? I'll give you 4 minutes. Does everybody know what I'm asking for? Find I of 0 minus. See if we have our thinking caps on. Find I of 0 minus, because we want to just make sure that that plot is correct. I think it was 192 milli. I will copy this. It's a little messy, but I'll copy it and put it right here. So find I of 0 minus. Give you one more minute. All right, who's got the answer?
I got 192.31 million.
192.31 milliamps. Anybody else get that? How'd you do it?
So since the switch isn't grown yet, that was just a series circuit. So I just added up the two resistances. So I got 260 ohms divided 50 by 260.
So essentially, you did that, right? All you did. So I of 0 minus is equal to 50 divided by 260. It was that easy. Not that useful, right? Because why do I care what the current through there through that point was, unless I was trying to see if it was heating up or something like that. But you know, I really haven't seen the capacitor's not even in the circuit. There's nothing to do with it. So make it easy. So 50 divided by 260, hopefully, and I think Luke said that that does match 192 milli. So you go 192, instantaneous change to 0.5. That's the other thing, right? Look at the curves. My voltage curve on my capacitor, which is I'm looking at capacitor voltage, can change instantaneously, and that is indicative of what I see at the top. On the bottom, I'm monitoring the current through a resistor, and the current through a resistor can change instantaneously. So at least there's maybe a theoretical limit in the real world. Nothing can really change instantaneously, but at least, you know, for the ideal world that we try to talk about here, it can change. So we start out at 192, we bump up instantaneously to 500 milliamps, and then we work our way down to 100 milliamps. Okay? Questions on this problem? All right, let's do the same thing for an inductor. Inductor is the exact same approach. The only difference is I'm looking for current for my initial condition. So I'm not going to look for VC of 0. I'm not going to look for VL of 0. I'm going to look for IL of 0. Same exact thing. All other things are valid. We know that in time, the current, not the voltage, but the current will achieve a steady state value that it looks like a short circuit and it doesn't change. And our equation, if it's going to be fully charged with a simple RL circuit, looks like that. We don't like simple, so 5 minutes. I'll give you 5 minutes to do some practice, unless you don't like to do the practice. Do you like to do the practice in class? Okay, give you 5 minutes to solve this problem. I already gave you the answer. So you can check your answer as you go. Couple more minutes. Okay, what y'all got? This is a problem that I'm hoping that you would not use your calculator at all. Because you don't need it, right? How did you tackle it? Unsure how to tackle it? Okay. What does 50 u of t look like prior to time t equals 0? What does 50 u of t look like prior to time 0?
0.
0. So while we walk up to the circuit and we don't know how long it's been energized, this power supply is not putting out anything. That's before time t equals 0. And what happens to an inductor in steady state? It shorts out itself. What happens to that 6 ohm resistor? It gets shorted out as well, right? Because no current goes to the 6 ohm resistor. So all you have initially is a 50 volt source in series with a 2 ohm resistor. Right? Can you see the short there around the 6 ohm resistor? It doesn't exist. I still show it there, but there's no current going through it. So that becomes 25 amps. Then in steady state, now I add in that second 50 volt source because it is time is greater than 0. So it's the same exact circuit as I had before, but now I have 100 volts across it as opposed to 50 volt. So now the current becomes 50 amps in steady state. The only thing I need to do is solve for the time constant. And over here, I'm looking out from the perspective of L. And I see a 2 ohm in parallel with a 6 ohm. Product over sum, 12 over 8, or 3/2. Then when I do my time constant, L over R becomes 2 seconds. So if I plug those into my equations, I of t, 50 plus 25 minus 50 e to the minus 2, t over 2. And 50 minus 25 e to the minus t over 2. Let's check that at the beginning. Are they the same? Are they the same? If I distribute the 50, right? Because I actually just did out the distributed out, but that becomes 50 minus 25 e to the minus t over 2, right? 8 over 4 is 2. Yes, they are the same. Did you need your calculator to divide 50, take 50 and divide by 2? Or 100 divided by 2? The product over someone was a little bit because it was a fraction, right? But if you kept it as a fraction, it wasn't so bad. Questions on this?
That secondary power source of 50 UTD, is that determined by that coefficient 50 after the time 0?
Yes, so U of t is just 1. And it only exists after time t equals 0. So it's 1 after 0 and 0 before 0. So 50 times 1 is 50.
Right.
Yep. That's all it is. And I'm trying to introduce the concept of unit step because we need to take advantage of that for our next chapter when we do Laplace. It makes things really important for us. Here's our final plot. Starts out at 25 and works its way to 50. In 5 time constants, which is here, it's within 2 to 3% of its final value. So again, you could go run this out for forever and it never gets to 50 amps, right? Because it never truly becomes a short circuit. But for all intents and purposes, we can say after 5 time constants, that's correct. What happens if you started doing stuff with pulses? Well, you can build pulses. You can take capacitors or inductors, and instead of like our condition over here where we're going for, instead of a unit step, you can actually have a switch, open, close, open, close, open, close. You can actually get very different looking waveforms. In the first case, and it doesn't say if it's a capacitor or inductor, but it can be either one. It just would be voltage or current. But in the first case, we've allowed that either the capacitor or inductor to fully charge. How do we know? Because this is flat, right? It ramps up, looks like an exponential. It flattens out. And then at some point, the switch transitions and you can see it's completely discharged. If you want to switch it to, all right, I want to keep this charged, like in the case of a bridge rectifier, right? Everybody know a four-wave, a full of either half or full wave rectifier bridge? You want to make sure that you don't completely discharge the capacitors across your bridge. You can see that over here, right? You've got the positive sine wave that's gone ahead and charged up the capacitor fully. And at some point, that goes away, drops down because it's discharging. But then the sine wave comes back up, starts to charge again. And that's how you smooth out your waveform. Instead of doing something like this, right, that would drop off, it actually smooths that out. So that's where you don't discharge it. You don't give it enough time to discharge. So you basically added a DC. So when you say something is not being discharged, you're essentially adding an average value that's a DC value. In the other case over here, we can see that it's not enough time to charge or discharge. And you can see those instantaneous changes. So now we're looking at currents or voltages, right? Not the steady state values. And you can see how, you know, you're fully discharging. So you're trying to get up there, but it doesn't get there. And so it discharges. And then the other one, which is a build where it doesn't have enough time to charge or discharge. This is a case where it is charging, not all the way, you know, not fully getting charged, but it's not discharging. Its charging time is less than its discharging time. So you can see it keeps ratcheting up until at some point, it's going to look something like this because the previous cycles have allowed it to charge up. Okay. And so that's how you can pulse things on or off, just with either you can have a fast enough acting switch or you can use power electronics to make that move. Question on any of the stuff to this point, capacitors and inductors, because from this point out, it's going to be pretty much all new material. This point up to here, it was all review. Now we move to new material, if everybody's understanding where we're at. It's all just more and more circuit analysis, except for the next chapter. No questions? Because the next chapter, and I know you love it, is math. You don't love it? Boy, oh boy, is it math. It is a lot of math. But it will be a little bit challenging to get through this because there is a lot of going back to mainly Calc 2. But remember, Calc 2 is integrals. So one of the outcomes for ABET is being able to apply differential and integral calculus. And this is one of the most important classes to meeting that ABET outcome, because in all of your previous classes, how many derivatives and integrals have you done other than in calculus? One. Maybe one. You're going to have to do a lot, at least to get through this material. But it's okay. We'll actually make things easier, which is funny because ABET, which is who we're accredited by, and that's important that we maintain accreditation because it helps you become PEs and all that stuff. But one of the things that they say, again, is that they want you to apply integral and differential calculus. That's one of the outcomes that they want to see our students get. But most of the time, engineers spend all their effort trying to not do derivatives and integrals because you don't do them every day. You don't need to. Why bother? So this technique, Laplace, is essentially a mathematical technique so that you don't have to do integrals and derivatives. But to be able to use a tool successfully or effectively, you've got to get some practice with it. You got to understand how the tool operates to work it safely. Like, you're not going to walk up to a chainsaw and start, monkeying with it and hope you don't cut your fingers off, right? It's the same idea. If you use this mathematical tool, and if you use it the wrong way, you can get some pretty erroneous results. So we've got to spend a fair amount of time going through the math to make sure everybody is on board with the process. But we don't need to get crazy in terms of derivations. We will derive some Laplace tables and some properties. But we won't get into a crazy amount of stuff. And we'll see why as we walk through the semester a little bit. But a Laplace transform is basically taking something that is in a domain, if you will, that is requiring you to do differential calculus, so differential equations, and it's converting it to another domain that you no longer have to do any differential calculus. And so the transform that we do to go from that domain that requires differential calculus to non-differential calculus is the Laplace transform. This is called a unilateral Laplace transform. Why is it unilateral? Because our time starts at 0 and not at minus infinity. So the definition for transforming a function, f of t, in the time domain into the Laplace domain is to take the integral from 0 to infinity, take our time domain function, f of t, multiply that by e to the minus st dt, and integrate that over those limits. And when we've done that, we're going to have a variable in the Laplace domain called s, because you see, right, that's d, that's a t. And when we integrate it and we evaluate at our limits, we get rid of our t's, but we still end up with s's in there. So we have a new function in the Laplace domain that's called f of s. Notice the lowercase and uppercase. Lowercase f of t, most of the time I'll try to be consistent, but sometimes I make mistakes, is if a function is a lowercase letter, it is a time domain function. If it is an uppercase letter, it is a Laplace domain function. All right? So when you're looking at expressions, look for the upper and the lowercase, and hopefully you can see what that is. And so the nice thing is, once we're in the Laplace domain, t is no longer a variable. It's a fixed value. It doesn't change. It makes it very, very, very simple. So when do we use it? To solve differential equations. You've been writing differential equations, you just don't know it. Those first order circuits that we just did, Those were first order differential equations, right? We had a V of t equals e to the minus something. That was the solution to a differential equation to solve for the voltage across the capacitor. So we were writing KVL, but we were solving for it and not solving it with a differential equation. Over here, we'll use Laplace to do that. And it's really helpful because what we call feedback and control, again, you're working with real world systems. Feedback and control is a way of controlling real world systems that require you to do derivative or differential calculus. And if you've taken PLCs, everybody here is taking PLCs, maybe not, I'm not sure, maybe. But what is one of the most common controllers that you find in the PLC world for like a continuous process? You may have even done PID tuning. Maybe, no? Proportional integral derivative tuning. Jude or whoever you had at SMCC, they didn't cover PID or PI controllers.
Yeah, not that.
Not the math, that's okay. But we actually need the math to really truly understand what's happening. But a PI or PID controller is actually doing math internally, right? It's proportional, integral, and derivative, right? Those are differentials there to go ahead and be able to actively control a system. And so if we want to use feedback control effectively, we've got to be able to understand Laplace. So we can go into the Laplace domain by integrating from 0 to infinity f of t e to the minus st dt. We can also go back from the Laplace domain to the time domain by taking the inverse Laplace transform. And I'm not going to show you how to do that. We'll talk about it in a little while, but that's a very difficult process to go back from the Laplace domain to the time domain. So let's do our very first one. Let's find the Laplace domain transform of an f of t, which is equal to e to the minus t. And that's a pretty easy one, and you'll see why hopefully in a second. So I'm going to plug into my calculator the Laplace transform of e to the minus EET. E to the minus ET, sorry, e to the minus t is going to be defined again as f of s, and that's equal to the integral of 0 to infinity e to the minus t times e to the minus st dt. Well, I know when I have two exponentials that are multiplying to each other, I can just add those together. And over here, I notice that I have some t's there. So I can factor out t from here and combine those two separate e to the minus whatevers into one e to the minus. Now, you'll notice I am factoring out negative t here, not positive t, negative t, and you'll see why when you evaluate at the limits of integration. So if you don't remember, hopefully you remember from calculus, to integrate this right over here, this whole term that multiplies the t term goes in the denominator that multiplies the original function. So I have my s plus 1 in the denominator. That becomes e to the minus t times s plus 1. And then I have my negative number because technically there's a negative also associated with that. So the final integration is negative 1, s plus over s plus 1, e to the minus t over s plus 1. Now I got to evaluate at my integration limits, which means this upper integration limit gets plugged in first, and then I subtract the evaluation at the lower integration limit. So let me write this out a little bit. So this negative 1 over s plus 1, that's up front. That's going to multiply e to the minus infinity s plus 1. Then I'm going to subtract again the valuation at the lower integration limits. And that's what my integration limits are. The infinity comes from here, and the 0 comes from here because I'm evaluating it for t equals, right? Those are the limits of integration because I'm evaluating it with a dt there. So what is e to the minus infinity times s plus 1 equal to? Yeah, e to the minus infinity is always 0, right? So I've got 0 here. And what is e to the minus 0 times s plus 1 going to be? 1. So I have -1 over s plus 1 times the quantity 0 minus 1. And now it evaluates to 1 over s plus 1. Can you see why I factored out e to the minus t and not e to the positive t? Because if I had e to the positive t, those would become positive numbers, right? And these would both be negatives in here. And it's a lot less obvious to see that e to the infinity goes to 0, right? You just see e to the infinity, like, and the number looks like it blows up. So you always want to factor out a minus t when you do these evaluations here to get your results. So our very first Laplace transform is done. E to the minus t converted to the Laplace domain becomes 1 over s plus 1. How about the Laplace transform of a number? Let's pick it to be 1. Just 1. That's all it is. And we want this to be t greater than 0 because we want this to be a unilateral transform, meaning we start at 0 and above. We're not going to go to minus infinity because it makes it a lot more work. So we plug it in again. So we have 0 to infinity, 1 times e to the minus st dt. That just becomes 0 to infinity e to the minus st dt. We integrate the e to the minus st, which is this -1 over s, e to the minus st. Do I need to spell out the evaluation at the limits part? Everybody understand how I got these, or do you need me to do those again? Because for a lot of you, you haven't seen Calc 2 in what, 2 years-ish? Sure. So let's start over here. -1 over s. I just factor that out front, right? Because this right here, these integration limits are t equals. So -1 over s has nothing to do with t, right? So I can move that out and factor it out way at the beginning. It doesn't change. Now I'm going to plug in e to the minus s times infinity, right? Because that's the upper integration limits. And then I subtract from it e to the minus s times 0, the lower integration limit. And I've done evaluating at the limits. So now I'm actually going to plug in numbers. E to the minus infinity, 0. And e to the minus 0 is 1. So those evaluate to be 0 minus 1. And when I plug in, multiply by my -1 over s, I end up with 1 over s. Okay. Now, this is a subtle thing, but this is very important because a lot of students get confused. You're going to see this 1 over s very soon, but there's a difference. This here is an f of t. That's an actual input, isn't it? I'm giving it a function. I'm giving it a power source of 1. This is like a 1-volt source or a 1 amp source. This is a DC value of 1. So for this input of 1, my output into the Laplace domain is 1 over s. So a unit step input or a DC source input becomes 1 over s in the Laplace domain. That converts to 1 over s. Okay, I'm trying to highlight the fact that this is an input to your system. I've energized my system by plugging in a 1-volt power supply. Okay? So just kind of keep that in your back pocket as like the emphasis is on I'm plugging in 1. Oh boy. Taking the training wheels off, right? Let's do cosine of omega t. And unless you'd love to integrate by parts, everybody remember that? We will have to integrate by parts. But not on this one, because integration by parts is a lot of work and it actually doesn't help you on this one. You end up in an endless loop. So what we're going to do is we're going to integrate, right? Because we got to integrate cosine of omega t. That's the definition of Laplace. But we're not going to integrate the cosine of omega t. We would like to convert that, if we can, to get rid of cosines and maybe make it a little more simplistic. And so what we're going to do is use Euler's or Euler's identity. Pausing here for a minute. Does everybody know or have heard of Euler's identity? Been a while? When did you all hear of it? Last week in my class? Yeah, EET324. Who here has done AC circuit analysis? Not with me, but wherever. So you've all done Euler's identity time and time and time and time again. If I have a voltage source of 120 volts at an angle of 45, right? That's AC circuit analysis. You remember doing that? That's not really 120 at an angle of 45. If you wanted to write this mathematically correct, it's 120 e to the j 45. Your calculator actually does that for you. So when you work with polar numbers, right? These are polar numbers when you AC circuits, it has magnitude and angle. That 120 e to the j 45 is written as polar. Why? Because it has a vector that does something like this, correct? But how do I build that vector? I have a real part and an imaginary part. How do you get the real part? Sock it to me. Bad joke. Sockatoa, sock it to me, right? I know this is 45 degrees, and I know this is 120. So Sockatoa tells me the real part is equal to 120 times the cosine of 45 degrees, right? Oscar had a heap of apples, or Sockatoa. Never heard that one? I like Oscar had a heap of apples. It just sounds more fun than Sockatoa. But yeah, the cosine of 45 degrees is equal to the adjacent over the hypotenuse. Isn't the real part the adjacent of the angle? It's not the hypotenuse, it's the adjacent. So that's that term. The imaginary is 120 sine of 45, right? That's the opposite over the hypotenuse. So this is the real part. This is the imaginary part because I have that 90 degrees of separation, right? We call it, if we're doing phasors. Isn't that what we just did right there? M, which is 120, times the cosine of omega t, or cosine of 45 degrees, gives me my real part, plus j m, which again is 120, times the sine of omega t, 45 degrees, gives me the real and the imaginary part. So if you've been doing rectangular and polar conversions at all, you've been doing Euler's identity all the time. And in fact, in MATLAB, now I've got a keyboard here with lots and lots of keys on it, and I'm gonna ask you to help me enter 120 at an angle of 45 degrees in MATLAB. Everybody here has a fancy dancy calculator that you enter in 120 with a little angle sign of 45, right? But you got that? Anybody's calculator not do that? Even the TI-36, I think you can do it that way, right? I think so. As I say, I had when I was in high school back in the 80s, I had a cheapy calculator that had the angle and it could do that. And that was a Casio, whatever it was back in the day. But that is a pretty basic feature. I would imagine a decent scientific calculator, like a $10 calculator, I would hope would be able to do that. But again, I'm not certain of that. I just would imagine that that's the case. So let's go and see if MATLAB has the angle symbol for us. Thank you for opening that all the way up over here. All right, so I've got my 120, or I will once MATLAB wakes up. Where's my angle? That? 45? Yeah, that's 120 is 120 less than 45, right? You just said that's the less than symbol. So that's a logical 0. It's asking a question. Is 120 less than 45 is what you just told me. And the answer is nope, it ain't. So it is a valid syntax that you did, but that's not what I was asking. I want 120 at an angle of 45. So where's the angle symbol in MATLAB? Doesn't exist. How do I enter that in? 120 times E, which is exponent, is the exp. They don't use E, they use exp just to say it's a function. J times 45 degrees. Let's enter that in and see what we get. Well, that can't be right because we know 45 degrees, the real part and the imaginary part should be the same, right? Because if it's 45, that means it's right in the middle. So the cosine term has to be the same as the sine term. That isn't happening here. Well, here's the other thing about MATLAB. MATLAB only works in radian mode. 45 is in degrees. So if I want this to be in radian mode, I have to multiply my angle by 180 over pi, right? Or pi over 180, sorry. That looks like the real part and the imaginary part. So how do you enter complex numbers in your calculator? It's the same thing. Anybody here have a calculator? Try entering in 120 at an angle of 45 using the E to the J 45. See if you get it. Most of your calculators should do it. That's how MATLAB works. And I used to have a TI emulator on here, but I so never used the TI. I don't even actually have it anymore. So did you get that? What do you know? Your calculator has been tricking you into using Euler's identity. So you've been using it for a long time. Anybody else get what Henry got? Type in 120 E to the J 45. I don't even think you need to put it in radian mode. I think you can use your calculator in degree. That's what I did in MATLAB. And that's how your calculator should operate. You should get around 85 plus J 85. If you look at the end of my answer, you can see the I term is way at the end. So it might be a little bit hard to see, but that's the J or I term. Anybody else get 85 plus J 85? No, yes? No? You didn't get it? Okay. Henry got it. Anybody else get it? It should be literally, if you're entering your calculator, most of the time you have to use brackets or parentheses. So if you go 120 E to the J 45 and you enter that in, I think it should give you the same answer. Maybe not, but that's essentially what you're doing when you hit the angle button. Your calculator is sneaking in the E to the J term. No? And confused. Let me see. Can I use your calculator and see? It'll take me an hour to do that because I don't use these anymore.
I know it's if you put, second and complex, it'll give you like the angle.
I don't need complex. If I just go 120 E to the 45. Oh, that's raised to the power. Darn it.
How would you put the J?
Yeah, that's what
The J is.
The J is I.
I got.
J or I is the same. I'm trying to find J.
Oh, it's where it's high and E is.
I and E. Oh, yeah.
Press it.
Oh, I can't do it because I put E there and it's just scrolling through. So that one, I can't make that one work. But if you enter it in, you should be able to enter it in E to the J45. I don't know why it doesn't work. Because it's the same thing. It's the same process.
Yeah, it's saying data type error for this one.
Yeah, I don't know.
But I mean,
I'll-
you get this.
So what I did in MATLAB, you can see the last one, I did 120 times E to the J 45, and then I just converted it to radian mode or radians because MATLAB doesn't work in degrees. So that's what I did there to get the answer. Your calculator should be able to do that. Maybe it's outsmarting you. I don't know why, but anyway, whenever you've been hitting the angle button, that's what you've been doing. So we're going to use Euler's identity to go ahead and help us solve for the Laplace transform of cosine of omega t. So the first thing we're going to do is we're going to assume that we have m e to the j theta. We'll just make this 1 to make it easy for us. So then we have e to the j theta is cosine of omega t. Actually, I should say this is omega t, not theta, but we have e to the j theta is e to the cosine of theta plus j sine theta. And then if we do e to the minus j, let me fix this really quickly. Should be easy enough to fix. Let me clear off my marks because I can't make anything out. So e to the j, this is theta. That's theta. Oop. And we'll do that here. Here. And then we have this one and this one. All right, let's try that again. Okay. All right, so we can see that e to the j theta is cosine theta plus j sine theta, and e to the minus j theta is cosine minus theta plus j sine theta. Now I'm just going to go and look at my Cartesian coordinates. And if I have any old angle here, right, we call that theta. Minus theta lives over here. So we can see that the cosine of theta or the cosine of minus theta are the same, aren't they? They're the same number. And we see that the sine of theta or the sine of minus theta is the same magnitude, but they're in the opposite direction, right? So we'll add in cosine of theta equals cosine of minus theta, and minus the sine of theta equals the sine of theta. So now we can go back here and we can simplify. If we add these two together, we have cosine theta plus j sine theta plus cosine theta minus j sine theta. Goodbye, j sine theta. And now we have 2 cosine of theta is equal to that term. So my cosine of theta is equal to e to the j theta plus e to the minus j theta over 2. Now we can do the Laplace transform of that. And we put that in here. And what we end up with is much simpler because we can distribute those e's, right? So we have e to the j theta and e to the minus st. Now I can combine those two, right? So I just have one e term, and then I can integrate it there. So finish that off. So I have 1 over infinity e to the minus st. And again, I've converted theta back to omega t. And this is a lot of math, like I said. You don't have to be experts at it. But what I end up with is my f of s is equal to the Laplace transform of the cosine of omega t. So I just did the Laplace transform of the cosine of omega t with all this math showing you that it's equal to s over s squared plus omega squared. So cosine just becomes s over s squared plus omega squared. I know it's a lot of math, a lot of evaluation. I would encourage you to take a look at it because, again, you can see, and I wasn't going to sit here and just run through all that stuff, but you can see when I evaluated at the limits, stuff starts to cancel out. And then all the thing that I did over here, these are complex conjugates of each other, right? So that's just a simplification, and I end up with s over s squared plus omega squared. All right, I'm out of time. So any questions on Laplace? Yes, sir.
For the last.
Yep. Oh, hold on. It's thinking. Yeah.
You have j omega, where does the j come back into that?
Where do you see j omega? Right here?
Yeah, just.
Because theta is equal to omega t, right?
Right.
The j term comes from the fact that it's e to the j theta.
Oh, okay.
Yeah, so you actually go up one slide and you can see where the j term comes from. Yeah, over here, theta is equal to omega t. That's where I substituted it in.
Oh, so you just bring the t out.
Exactly. Because I still have to integrate it with respect to time, and it's cosine of omega t or sine of omega t, not sine of a number. It's a waveform, right? So the difference is a sine of omega t is a sinusoidally varying term, where the sine of 7 is a number.
Yeah.
So that's why we had to go back and substitute in the omega t to actually get a wave. All right, I'm out of time. Have a great weekend, everyone, and good lab tomorrow. I will see you next week. Take care, everyone.
Thank you, Paul.
Do we have
Hey,
lab
study
tomorrow?
session. Did Mark not post it?
He posted it. Hey, Drew.
All right, take care, everyone.